I think it's common sense to understand that if you stretch a rubber band with your fingers, you're going to feel a force trying to counteract the expansion of the rubber band. It's just as logical to understand that if galaxies out in the universe move away from one another, the force of gravity will try and pull them back together, just like a rubber band tries to pull your fingers together, or like gravity pulls you towards the ground when you trip and fall. The question is, does this actually happen to galaxies in our universe? And why or why not? This lesson will answer that question for you as we talk about the acceleration of the universe. Again, it seems that as galaxies fly away from one another, their movement away from one another should be slowed down by the force of gravity. But observations of redshifts of distant celestial objects have shown us that the expansion of the universe is anything but slowing down. Instead, the universe is expanding ever faster, meaning the expansion of the universe is accelerating and galaxies are moving farther apart. However, such an acceleration cannot come out of thin air. There has to be a force that counteracts the force of gravity, trying to spoil the acceleration party. In our rubber band example, that force was generated by your fingers fighting against the rubber band's desire to contract back down to size. In the universe, the force repulsing gravity is far more mysterious. This mysterious force is called dark energy, a form of energy opposing the force of gravity, which causes the expansion of the universe to accelerate. Astronomers have come up with more than one theory for what form dark energy takes, or which method actually drives the accelerated expansion of the universe. For instance, in the early 20th century, Albert Einstein came up with something called the cosmological constant. This anti-gravity property of space, proposed by Einstein, essentially suggested that the universe is filled with a type of energy that, on its own, makes the universe expand. I always like using springs to bring this point to life. If the force of gravity is your hand pushing down on a spring trying to contract it, then the basis behind the cosmological constant is the expansive force of the spring itself. That's the simple gist of it. Another form of dark energy is known as quintessence, a dynamic form of dark energy. This is a supposed form of dark energy that fills completely empty space, the vacuum, and causes the acceleration of the universe. The big difference between the cosmological constant and quintessence is that by the term itself, the cosmological constant remains constant with time. In other words, the universe will have undergone this acceleration throughout its entire history. This notion is in contrast to quintessence, whose effects may not necessarily be strictly constant over time. Regardless of which form or method drives the acceleration of the universe, we know it's there. And because it's there, it has important implications, one of which we'll discuss now. Prior lessons on inflation and models of our universe pointed out that our universe is flat. In order for our universe to be flat, its density must equal the critical density. The critical density is the average density of matter and energy that is needed to make space flat as opposed to curved. But we know that the density of ordinary, that is to say baryonic matter, and dark matter in our universe is not nearly enough to equal the critical density. Dark energy is what helps to fill in the voids, so to speak, and helps explain how our universe has enough matter and energy in tandem to make the universe flat. Using Einstein's famous equation E equals mc squared, we know that matter and energy are equivalent. Therefore, dark energy is equal to a certain amount of mass spread about space. When you add dark energy to ordinary matter and dark matter, the density of our universe equals critical density, and we know this means our universe has to be flat. Thus, we now approximate that our universe's density is made up of 71.4% dark energy, about 24% cold dark matter, and approximately 4.6% of ordinary matter. This lesson discussed the mysterious dark energy, a form of energy opposing the force of gravity, which causes the expansion of the universe to accelerate. More than one proposed form of dark energy may exist. There's the cosmological constant, an anti-gravity property of space proposed by Einstein, and quintessence, a dynamic form of dark energy. The main difference I want you to remember between the two is that the cosmological constant is, well, constant, meaning the universe will have accelerated throughout its history, whereas with quintessence, this acceleration may not have been constant. The other important thing I want you to remember is that dark energy helps to explain how our universe's density can equal critical density when there's not enough ordinary or dark matter to do so. In order for our universe to be flat, its density must equal critical density. The critical density is the average density of matter and energy that is needed to make space flat as opposed to curved. When combined with dark matter and ordinary matter, dark energy helps to bring our universe's density to this critical density and explain why our universe can be flat.